Hello everyone, we are group 5 from section 3. Our topic of the project is the influence of release angles on swing. There are 5 of us which are Lizian, Fujue, Yongda, Abdallah and also me. Our report involves introduction, objective, case study, methodology, calculation, discussion, conclusion and also reference. So first I'm going to talk about introduction. As we know, swing is common playground equipment that provide a real-world example of how energy is transformed and conserved in dynamic system. So we know that the swinging of a pendulum is a famous illustration of simple harmonic. So we inject the same idea of pendulum in swing. We know that the law of conservation states that energy cannot be created or destroyed, but it can transform from one to another. So in the experiment, we assume that there's no energy losses due to non-conservative forces like air resistance or friction. After we assume there's no energy losses, then we calculate the velocity of different angles using conservation energy formula and height of the swing. The experiment aspect will be the height of the swing and also the wear. So yeah, from the slide we know that when the swing is released, the swing will be in three motion which are point A, B and also C. So at point A and C, the swing has maximum potential energy and minimum kinetic energy. So potential energy is close to mgh. M is mass of the object, g is the acceleration due to the gravity, and h is the vertical height from the lowest point. So at point B, the swing has maximum kinetic energy while the minimum potential energy, so brings the formula that kinetic energy is equals to 1 over 2 mv squared. M is mass of the object and v is the final velocity of the object. So the total mechanical energy is the sum of potential energy plus kinetic energy, as there is no air resistance or friction at the point, so brings the formula that 1 over 2 mu squared plus mgh equals to 1 over 2 mu squared plus mgh. So u is the initial velocity of the object and v is the final velocity of the object. Next, we discuss about the objective part. So first one is when the swing is displaced and released, it will accelerate towards the equilibrium position due to the component of gravitational force acting along the swing's arc. So we have to determine the potential energy and also the kinetic energy at various positions when in the motion and to verify the conservation of mechanical energy in the motion of swing. By using Newton's second law, we have to determine the periodic motion of swings, whether it's translation, rotation, or general plane motion. Last but not least, we analyze the length of the swing when the swing at different positions with different angles, like we use 30° and also 50°, and we analyze also the forces and motion involved in the swinging motion.
Not only is it important educationally to understand the mechanics behind swing motion, but several applications dealing with gravitational potential energy, pendulum motion, and the use of damping will be realized in real dynamic systems. The main factors affecting the performance of swing include its length, the initial angle of displacement, and any external forces such as air resistance and friction. Initial angle of displacement is one of the case studies. The angle at which the swing is released, otherwise known as the initial angle, also plays a critical role in how high the swing will rise on the opposite side of the arch. A larger initial angle increases the total gravitational potential energy at the start, possibly allowing a higher swing on the return. However, large initial angles introduce nonlinear behavior, especially in circumluminous of larger.
So now I will go into the methodology parts. This report investigates the principle of the energy transformation and conservation in the pendular system. Uh, this demonstrates turns the motions of a playground swing. So a standard playground swing is used to simulate a pendulum tap. Okay. Uh, this methodology adopts a systematic approach to observe, measure, and analyze the energy dynamic within the system. Um, so in our experiment, the key of the parameters such as the length of the strings from the pivot points and the mass of the object in motions are recorded. A protector measure the angle of displacements while a stopwatch is employed to determine the period of the oscillations. The swing is replaced to a no angle and released without additional force. Observation focus on the key point in the motion circuit. Maximum displacement, equilibriums, and the transition in between. The speed and height of the swing at various positions are recorded using the standard kinetic equations. To greater natural motions, the swing was displaced to a precise angle of 30 degree and then softly released without the need for extra power. Ah, okay. So the energy values at the various points of motion will calculated, which is potential energy is equal to the mgh, while the kinetic energy was determined at the equilibrium using the uh, 1 per 2 uh, multiple with the m and multiple with the velocity square velocity. Okay. So the experiment also will be repeated with a 50 degree to ensure a dose investigate of the energy transformations and conservation in a pendular system. This all for the methodology part.
My name is Lorena. I present the result parts. Since we cannot to get the actual angles to release the swing by the projectors, so we are using the trigonometry functions to calculate out the distance based on the angles 30 and 50 degrees. After you calculate out the 30-degree angles is on the distance with 0.725 meters, and the 50-degree angles is the 1.110 meters. Then to calculate the velocity, we have using the distance over time taken. And in this experiment, we have fixed 2 points, which is the in the distance of 0.5 meters. And every angles, we have 3 times of the time takers to calculate the average time. Then we can get the 30 degree of angles is the average time on 0.43 seconds, and the 50-degree angles is the 0.18 seconds. Then after that, we can get the velocity. There is the 30-degree angles is 1.163 meter per second, and the 50-degree angles is the 2.778 meter per second. Then for cover the theoretical results, we are using the conservation of energy, which is the 1 over 2 mu squared plus mgh equal to the 1 over 2 mu squared plus mgh. Then we can get the theoretical result on 30-degree angles. There is the 2.192 meter per second, and the 50-degree angles is 3.338 meter per second, and we can compare it with the experimental result. To calculate the tension of the strings, we are using the formula on the gravitational force plus the centripetal force. And first, we calculate the gravitational force. We can get the 188.6 meters. Then for the 30-degree angles, the experimental centripetal force is 55.97 newtons, and we can get the tension on 644.57 newtons.
And after that, we calculate the theoretical result for the angles, 30-degree angles. The centimeter force is 198.82 newtons, and we can get the tensions on 787.42 newtons. Then for the angles on 50 degrees, we can get the experimental result on the centimeter force is 319.34 newtons, and we can get the tensions is the 907.94 newtons. And for the theoretical result for 50 degrees angles, the centimeter force is 461.06 newtons, and finally we can get the tensions on 1049.66 newtons.
So my name is Li Zhixian. So right now I'm going to present about our discussion. So let's explore the swing motion and the angle of release. Increasing the release angle leads to a more significant horizontal displacement, but reduce the vertical height, shorten the average swing time, and increase the velocity. For example, at the release angle of 30 degree, the velocity is 1.163 meter per second, whereas at 50 degree, it increased to 2.778 meter per second. However, comparing the experimental and theoretical result, we observe discrepancy. Experimentally measured maximum velocity are lower than theoretical prediction. This difference arises due to air resistance, opposite motion, friction at the pivot point, reducing energy transfer, and other energy losses like damping. On the other hand, theoretical calculation assume no air resistance or friction and perfect mechanical energy conversion, making them idealized approximation of reliable condition. And that's all for me. Thank you very much.
Okay, we will go through the conclusion. This research in energy transformation in the pendulum motion has indeed yielded worthwhile lessons regarding the principles of dynamic and further the laws of Newton and the law of on the conservation of mechanical energy. A swing, though the simplest in application, actually serves out as a classic example of smoothly transmitting status between potential and kinetic energy and working wholly under the laws of classical physics. At its pinnacle of travel, all of this energy is in stored potential energy because of the heightened position it assumes as it lowers and swings faster. This potential energy is gradually converted into kinetic energy until it reaches a maximum at the bottom of the arc. This repetitive energy conversion reinforces that the energy within an exalted system does not change, as dictated by the principle of conservation of energy. Thank you very much. Assalamu alaikum.